Jnanam Paramam Dhyayam. Knowledge is supreme.
Okay. So, remember, for arbitrary ring A, the cool dimension of A, we have seen it is the supremum of dimensions of A localized at P. This supremum is running over prime ideals. So, in order to compute this or understand this, one want to concentrate on the each localization. So, therefore, sometime onward, now we will assume we will concentrate on local rings. So, local rings. So, that is a ring, commutative ring with only one maximal ideal, that is also denoted by M, and M is the Jacobson radical of A. So, Jacobson radicals are usually denoted by M suffix A, that is intersection of all maximal ideals, and also now there is only one residue field. So, that residue field is also sometimes denoted by K suffix A. So, we have such a local ring. This is the maximal ideal, this is the residue field of M. Now, from this I want to get a graded ring, standard graded ring, and apply this Hilbert the Poincare series, and then before I forget, this integer d we got, we want to prove that is the dimension, that I have not yet proved. So, that is I will prove this d is actually the dimension, and then how am I going to go further? So, for this local ring, from a given local ring, I will attach a graded ring, and then for that graded ring we have this theory of Poincare series and so on, and then we get the integer out of that, and that integer is nothing but the Krull dimension. That is what we will prove. So, in particular, what we would have got as a consequence, in particular, Krull dimension of a local ring is actually an integer, so finite. So, but that does not show that Krull dimension of an arbitrary ring, arbitrary commutative ring, even assume Noetherian, that it is finite. In fact, that is not true. So, because it is a supremum over these integers, and these may be increasing. So, also I will show you examples of Noetherian ring with infinite Krull dimension, with infinite Krull dimension. Construct examples of Noetherian rings with infinite Krull dimension. This, for this kind of treatment, you will see a book by Nagata, local rings. In fact, only reference I know is this book. Only these books deals with such examples, and actually this book is one of the early book, and this book is not so easy to read, but on the other hand, the material this book contains you can't find any other book. Okay, so what is the graded ring which we define out of the local ring? So, that is called the associated graded ring. Graded ring of a local ring. That is the following. So, we have A local A and M. M is the maximal ideal. So, you put K equal to A by M, and then put AM. So, put M power n by M power n plus 1. Now these are annihilated by m. So therefore they are a by m modules. Right. So I can form their direct sum. These are modules, this is a field. So I can look at a by m, direct sum m by m square and so on, direct sum m power n by m power n plus 1 and so on. And this now we have to, right now we have only a direct sum of abelian groups. We want to make it as a ring. We know also each one of these component is actually a vector space over a by m. So this standard notation for this is gr suffix m a. This is called the associated graded ring of the local ring AM. Now what is the ring structure there? So I only have to give you how you multiply the elements, right. So if you have one element x bar in m power r by m power r plus 1, this is homogeneous element of degree r, and also other one y bar in m power s by m power s plus 1. Then I want to multiply them. So first you multiply as usual x y. Now what does this x bar is here means? That means x is an element in m power r, and this x bar is the image modulo m power r plus 1. Similarly y. So x y as usual, this will be an element in m power r times m power s, which is contained in or equal to m power r plus s. And now I take its image in, when I write x bar times y bar, this should be x y bar in m power r plus s modulo m power r plus s minus 1, no, plus 1. Take the image there, and now we will have to check this definition is well defined. So check that with these definitions, this GRMA is a graded ring. In fact, standard graded A by M algebra. So actually really the theory I will use in this particular case is only for when R naught is a field, but for more general applications I will not only do this concept for the maximal ideal, but the powers of maximal ideals, or not even powers of maximal ideals, but so called M primary ideals. So more generally define GRQA for arbitrary M primary ideal Q, and that will be now graded A by Q algebra, standard A by Q algebra, standard A by Q algebra. Now see here, this A by Q is not a field in general, but it's an Artinian ring because you have gone modulo primary ideal. So there is only one maximal ideal, it's an Artinian ring, and there is dimension 0. So therefore it is an Artinian ring. So length makes sense and so on. So then one applies the earlier theory for this graded algebra, and then we will get the Hilbert polynomial, and then we will get the degree, and we will get those integers and so on. So, I will continue next time with this more general setup, and use standard examples of the graded ring usually arise from a local ring. So, if you have a local ring AM, local ring, then to this local ring we associate this new ring which is R A by M, direct sum M by M square, direct sum so on, direct sum M power N by M power N plus 1 and so on. So, this note that this each component here, so this is a direct sum of abelian groups, but each component here is actually annihilated by M, therefore, they are also A by M modules. So, therefore, this is indeed ring, and the ring structure is, the addition is clear because it is a direct sum of abelian groups, and multiplication is, if you have an element x bar in M power R by M power R plus 1 and another one y. So, to define a multiplication I only have to define it on the homogeneous components and then extend it by distributive law. So, this is, if I have two elements like this, so you take a lift here, that means you choose x so that x belong to M power R and y so that y belong to M power S, and you multiply them as in the ring and take its residue class. So, this is the residue class of xy in x, because x is here and y is here, the product will be in M power R plus S. So, take its image modulo M power R plus 1, and here check that this is actually a graded ring and it is generated, it is a standard graded ring. So, this is called associated graded ring of A with respect to M. So, GRMA is a standard graded A by M algebra, and nothing special about M, but we could do it little bit more generally. So, what we could do is, if you have a local ring A M, local ring, and we have a primary ideal Q, Q is M primary ideal. So, that means this ring A by Q is actually Artinian ring. And then we, instead of M, we can repeat this, the above process for Q. So, associated graded ring of A with respect to Q is denoted like this, GRQA, this is A by Q, direct sum Q by Q square and so on. So, this is a standard graded A by Q algebra, and now A by Q is Artinian. So, we have the Poincare series because A by Q is Artinian and so on, and that is a numerical function which is a polynomial function of degree. Now, this is standard graded algebra generated by this component. So, that will depend, that is the number of generators for this as a by Q module is precisely the minimal number of generators for Q. So, minimal number of generators for Q, this is if you have the generators, minimal generators for Q x1 to xn in Q, then this is R n. So, you get a polynomial function of degree less equal to n minus 1. So, that polynomial function arose from the Poincare series, that is the function m going to length of a by q module q power m by q power m plus 1, this function. And then when we want to do the integration of that will increase the degree by 1. When I say integration means the operator f to df and the other way, from df you can get f. So, okay, so that polynomial usually denoted, so HQM, more generally HQM for any finitely generated, M is finitely generated A module, and Q is primary ideal, then HQM is the function from Z to Q, which is defined at every M. It goes to length of Q power M modulo Q power M plus 1 times M, and then this is a polynomial function. So, for large M it will agree with a polynomial with rational coefficients, and that polynomial usually will be denoted by PM, PQ, M. So, this is a polynomial with rational coefficients x, so that they agree for large. Actually, there is a slight a twist in the notation, that for when I say PQ, I usually consider not this function, but the integration of that function, that is M going to length as a by Q module of M by Qn plus 1 Qm plus 1 times M. So, when I add up this up to M, they will get this coefficient, because the length gets added like that. So, if I would have considered for this function, then the d of this will be so. So, this in this notation, this HQ M at any M will be d PQ M at M for large M. So, when I differentiate it, I will get this formula for this. Okay. All right. So, the theorem we have proved is this PQ, the same notation as above, PQM is a polynomial function of degree less equal to mu q, where mu q is the number of generators for q. Because if I have a minimal set of generators for q, then they will their residue classes mod q square will generate the associated graded ring as a standard graded algebra. Okay. So, we can write down a proof for this again. Proof. Okay. So, we are putting R equal to GRQ A and N equal to GRQM. So, I have a graded ring and I have a graded module, and we have the right assumption A by Q is Artinian This is standard graded generated by the residue classes of the minimal set of generators of Q mod Q square. So, in that notation this Hn is a polynomial function of degree less equal to mu q minus 1, because we are considering, when I said H1, that is H0. You remember H1 was a integration of H1. So, therefore, if you take this one dq dpq of m, which is HQFM, which is HQ of n. So, this is a polynomial function. So, it is a polynomial function because this HQ is a polynomial function of degree less equal to mu minus 1. This one PQ, so I should write here, that implies PQ m is a polynomial function of degree 1 more than this, less equal to mu q. Okay, so now a couple of observations, like now what happens to the leading coefficient. So, that is the lemma. Lemma says the degree, we know degree is less equal to the minimal number of generators for Q. So, the degree of PQ m does not depend on the m primary ideal Q. So, that means if I take a different primary ideal, then the degrees will be the same. So, proof, observe that Q is m primary and m is maximal. So, that should imply that some power of maximal ideal will be contained in Q. And therefore, the nth power of r power n, m power r power n, m power r n is contained in Q power n. I should write m actually, m, this is contained in m power m, and therefore, when I take PQ of m at this Rm minus 1, this is the smallest. So, this length will be the biggest, and that will be bigger than this PQ m of m minus 1, and this is bigger equal to Pm m minus 1. So, I have these polynomial functions and there, so that shows the degrees. So, this one and this one, so that will show that this Pm PM M and PQ M have the same degree. They are polynomial, all these are polynomial functions, and because of this inclusion, this bigger equal to thing, their degrees will be same. Yes, this should be PM. This is coming from here, no, this is PM. Yes, thank you. So, these two polynomial functions are whatever degree is, when you substitute the variable to be equal to r times m and it's bounded, this polynomial function is in between them, therefore they have the same degree. Leading coefficient changes. So, actually leading coefficient also we can keep track. So, what this lemma says that the degree of this PQM is independent of Q. So, therefore, that is an invariant of M. So, the degree of PQM, this is usually denoted by TM. This is invariant of M, it does not depend on the ideal Q. Okay, also a simple observation like what we did earlier for a graded ring, if you have an exact sequence of modules, short exact sequence of, so all this discussion goes under the assumption that A comma M is a local ring, and all these M prime M double prime are finitely generated modules over A. This is a short exact sequence of A modules, then the degree of PQ middle plus degree of this plus, so plus minus plus, right. So, degree of this, degree of PQ of this is M prime, this is M double prime minus PQM, this degree is strictly smaller than degree of PQM. Remember this, in such a situation when you take the Hilbert series, it will be alternating sum is 0. So, from that you get, so this is coming out of the alternating sum, and the degree is strictly smaller than the degree of this. So, again we have proved this, but again you can write the proof. So, proof, we may assume M prime is non-zero, otherwise these are isomorphic and there is nothing, and Q we can put this inside thing, put Q is this PQ M prime plus PQ M double prime minus PQM. So, now this sequence will induce a exact sequence like this. When you tensor with A by Q power n plus 1, a tensor product is right exact but not left exact. So, when you start writing the long exact sequence, this is M double prime Q n plus 1 M double prime to 0, then here it will be M by Q n plus 1 M, and here will not be exact. So, but I want to make it exact, so to compare the lengths. So, this is M prime by M prime n plus 1, and I want to put a 0 here. where m prime at n, this will be actually q m prime, this m prime, and intersect with the kernel of that. So, intersect with q power n m. This is m prime n. So, when you intersect with the kernel and go mod the next one, this is exact. So, this is exact, and then you compare the lengths. So, that will give you q p q m prime from here minus f, where f is will come from the length here, where f at n will be equal to m prime modulo m prime n plus 1. And now here to continue the proof, I need so called Artin-Ries lemma. Yes. Oh, so this is the length. This is the length. Sorry, this length is same as summation length of m prime I modulo m prime I plus 1, and this is I up to n. So, when I take the sums, when I from this exact sequence, and I take the length and then add up. So, this here I will get PQM, here I will get PQM double prime, but that difference, this is with the plus sign and this is with the minus sign, then that difference will be coming from here, that is what our Q is, and that therefore is Q will be equal to the difference of what I wrote this function and that PQM prime.